This video I'll be working through question 2 of the 2018 scholarship exam. Right, question 2. Interference. State the conditions for stationary interference fringes to be produced by two sources of light at distance d apart. So I'll pause, write the answer and discuss. Right, so what I said is, first I put the formula that describes 2-point interference. So if you have two light sources, I'm just going to draw all over this. You have two light sources. It's got to be monochromatic. So monochromatic meaning mono, meaning one, chromatic meaning color. So one color. Otherwise, the interference pattern you'll get like a rainbow effect. So the wavelengths must be the same. What else you need? Constant phase difference. So if you could change the phase of one of the, so let's assume these are two waves where my fingers are the antinodes. So two waves coming together, when they combine you get constructive interference. If they're half a wavelength out of phase, when you combine them, you get complete deconstructive interference. So if you could have if the phases weren't constant, this one could be moving back and forth, so it would oscillate between constructive and deconstructive interference. That's what it means by constant phase difference. The slit separation, or the separation of the sources, so there's a distance from here to here. I say slit separation because that's probably what you're used to, but just literally the separation of the sources needs to be greater than half the wavelength. It just needs to be greater than the wavelength. And the amplitudes must be similar. If you have one that's really, really bright and one that's really, really dim, you're not going to see anything. So I've chucked that in there. Right, so two narrow slits separated by a distance d, these two here, illuminated by light source, incident angle phi, as shown below. Light from the two slits produce an interference pattern on the screen. L away, assume that L is much greater than D, otherwise it wouldn't really work. Otherwise you need to use trigonometry, because that L, it's a trigonometric approximation. I'm pretty sure it's tan theta. Anyway, if D is equal to that really itty bitty number, 0.1 micrometers, and wavelength is red light, 633 nanometers, calculate the smallest angle phi that will give an intensity of 0 at point P on the screen. So we'll assume that we'll write the formula first. So you got D sine. Can we see that? Yeah. D sine phi is equal to n lambda. So point P on the screen, I'm assuming that's pretty much the center, or just offset from the center, I should say. So this is the first. I'm assuming here's the center here. Yeah, I'm assuming this here must be the first dark spot. So this is the first nodal line. Nodal line means no wide. So this is the first dark spot. So that is when the path difference is a half. So here's the center line. The center line is always a bright spot, because that's where, assuming there's a symmetrical, here's the center line, that'll always be a bright spot. So we're looking at the first dark spot, and we're trying to figure out what's the smallest angle theta can be. That'll give it an intensity of 0 at point P. So what we have is d sine theta equals n lambda, and this theta is related to the path difference. So I'm going to rearrange this a little bit. So theta is equal to sine inverse lambda over 2d. Right, we know what everything, and that is equal to, what is that equal to? It is simply equal to sine inverse, this is the first nodal line, so it's going to be half, lambda is going to be 633, 3 times 10 to the negative 9, divided by 2 times 1.0 times 10 to the negative 4. And that gives me equal to 0.181 degrees. There we go. So that's the smallest angle for the first order minimum. Cool. Next question. Another way to produce an interference pattern is to illuminate a small wedge-shaped air gap as shown on the diagram below. When viewed from an angle above, alternate bright and dark fringes are observed, dark spots, fringes, whatever. The horizontal distance to the nth fringe, dark fringe, is x. At this point, the thickness of the air gap is equal to t. Note, when the light is travelling in air, it reflects off the glass. Reflects off the glass, it undergoes a 180 degree phase change. So it basically means when the light reflects, let me see that from here, when it reflects off the glass, there's no phase change. And when it reflects from air off glass, there's a phase change. So here there's no phase change, here there is a phase change. So this and this will be 180 degrees out of phase. Assuming the path difference here is 1, that would give you deconstructive interference, and so on and so forth. So this whole situation is kind of confusing. I'm going to post 2 things in the description. One will just be like how this whole thing sort of works. Another one will be a link to diffraction of these type of gratings, if I can find it. If I can't, well then too bad, but I'm pretty sure I'll be able to find it. So you can sort of think of this as a whole lot of light beams coming in. You got a whole lot of these light beams coming in, and at each point it bends, and then goes to this glass and bounces off. But you get to a point where one will come in, if you're looking straight down. So here we go, from directly above position A marked in the diagram, a dark fringe is observed. Why is this? So assuming this air gap is still there at A, which is basically here, we're looking down, we're down, it should be a straight line, but it's not. Assuming half the light will reflect at this boundary here, the inside the glass, half is going to reflect there, and the other half is going to go through and reflect like it is here, but all crammed in. So half of it is going to have a 180 degree phase change. The other half is just going to reflect in the glass and bounce straight back up. So if you have half the light that's not out of phase and the other half that's 180 degrees out of phase, you're going to get a dark spot. So I'll pause it, write the answer, and then continue. So I've said at A there is negligible path difference because this distance here is apart, well, from here to here, so here's T, this distance here, assuming it's really, really small and you can just pretend it's T, from here to here is half the path difference because you've got to go there and back. At A there's like no path difference, it's basically crammed together. Wave 2 is 180 degrees out of phase, so this one here is 180 degrees out of phase because that's the one that flips on the air to glass boundary. From phase 1, destructive interference occurs and a dark fringe is observed. So, next one. Light of wavelength 550 nanometers, that's yellow light, or yellowy green, is incident normally on air gap of that's an angle theta. And this is in radians as well, so you have to change your calculator to radians if you're going to use trig, which we will be doing soon. Calculate the number of dark fringes observed per meter. So, essentially, if you're viewing this above here, so here's your eye, up here, I don't know how to draw an eye, I'll just put like a pupil in there. There's your eye, you're observing, and here's like a meter, you're observing how many of these spots from these beams of light are going to be in a meter. So that's how many, that's basically what we're looking for. So, how we are going to figure that out. So we're going to draw a little sketch of this here, further down so we can sort of see it. So we have X, that's this line here. We have T, that's this line vertically straight up. That's essentially the path difference, approximately. Because it's a really small difference. You can sort of just, even this is on an angle with such a small amount, you can just, the vertical amount can be T. Then we have the angle theta. We have X, and then we can say that tan theta, because we have the opposite and the adjacent, is equal to the opposite, which is T over X. Well, X is our horizontal distance. We're just going to make X 1 because it's 1 meter. We're going to find out how many of these little fellas are going to happen per meter. So we are going to rearrange. We're going to find T. So T, tan, we're at what, 3.5? 5 times 10 to the negative 4 radians times 1 meter is equal to, it just so happens, 3.5 times 10 to the negative 4. I'm not even sure what the units are for that. And that is equal to t. So, there we go. So we've found what t is. It should be, was it angle per meter, or angle meters? Anyway, and that's the fact that these are the same number as a small angle approximation. If you have really, really small numbers in tan, sine, or cos, they end up being the same thing. Right. We know that the path difference has to be 2t, because we're going to go down here and then back up. So when I say path difference is how far the difference in distance that wave 1 travels comparatively to wave 2. So that path difference is 2 times t, because you're going to go down and then up again. So I'm going to call it PD, path difference, is equal to 2t. We'll get onto this soon. And that is equal to 2 times 3.5, that's easy. 7 times 10 to the 4 meters. Well, that is in meters, isn't it? The unit for that is meters. And that will be equal to n lambda. This here is essentially the path difference. That tells you what the difference is between the waves. Because if you divide this number here by the so this number here by the wavelengths, if this is a whole number, that'll tell you, if this number was 5, it'll tell you the path difference between the two waves is 5 whole wavelengths. Which means if the path difference is 5, it means you're going to get 5 antinodal and nodal, because between each whole number is a half, which is the nodal lines. So all we're going to do now is just go n, so the number of dark fringes, we'll think about the bright fringes for now. So the number of fringes in general is going to be equal to 7 times 10 to the negative 4 divided by the wavelength, which is 550, times 10 to the negative 9. And that is going to be equal to 1,272.7 7 fringes. And we've just got to remember that this is going to give us 1,272. Half is a dark fringe, so it's going to give us basically 1,000, because if this was a whole number, that would give us to the next bright fringe. So it's really, which is equal to 1,272, well, that's 3 dark fringes. Dark fringes. Because I'm going to write because CAUS half is nodal. How do you spell nodal? Nodal. There you go. Because 1,722.5 is that, is up to that last. So you got 1,200. Between each number is a half number, so you got to add them all together. And then we've got this half as well that it adds onto. So there would only be 1,272 bright fringes, but there'd be 1,273 dark fringes, because we're going past a half. There we go. Hope that explains things. Right. If the angle is wedge-shaped, is a wedge-shaped ear gap, theta becomes too large. No fringes are observed. What's happening? So if we increase this wedge here, it's telling us that you can't see the fringes. Well, we can see sort of from this formula that as you increase theta, t increases, because we can see that here. As t increases, the path difference increases. So as this number increases, this number on the numerator, not the denominator, the wavelength is kept fixed. So this number here will increase. If you increase theta by a huge amount, t increases by a huge amount, the path difference will increase by a huge amount, which will mean the number of fringes will increase by a huge amount. And if there are too many fringes in a set amount of distance, your human eyes will not be able to distinguish them. And maybe like a microscope will be able to, but not your eyes. So I'll pause it, write the answer, and then discuss it. Right, so I've said as theta becomes larger, the number of fringes per meter, I should have really just said per unit length, but we've used Prometheus up there. The fringes become so close together it is unresolvable with human eyes.